Hey, it's Dr. J. I'm back with a great story about exponential growth. I heard this one recently. I think I'd heard it before, but I heard it again recently, and I really wanted to share it with y'all. And this is a true story. I didn't just make these numbers up. In 1946, the Argentinian government brought 20 beavers from Canada. Their goal was to revitalize the economy. There was, hard times, and they were looking for a way of stimulating the economy. They could hunt the beavers, perhaps sell them for meat, use the fur to generate a fur industry, and they thought it was a brilliant idea. So they brought these 20 beavers and released them into the wild. And these are Canadian, North American beavers, and they brought them down to Patagonia, the tip of South America. It was done by the cooperation with the Chilean and Argentinian government. I won't get too much into the details. I want to stick to the math. But I will at some point tell you the bad part of the story, other than what happens to the beaver population. The beavers grew out of control. And by 2011, there were 200,000, it was estimated to be 200,000 beavers living in the wild in Patagonia. As you could probably imagine, the experiment failed. People did not hunt the beavers. They did not like the meat. The fur turned out to be very rough and coarse and did not make nice, pelts as they would in the North American beaver. So they sort of adapted to the climate in southern South America, the southern tip of South America, and basically evolved into a different creature. They got larger, they got tougher, and they didn't have any natural predators. There was nothing to eat the beavers. And so they just kept growing and growing and growing. So this is an example of humans messing with the environment and causing everything to get out of control. And it makes a great example of what we've been studying with exponential growth functions. So a couple questions I'm going to ask. I'm going to ask for the doubling period. So they started off with 20 beavers. How long did it take for that to grow to 40 beavers? All right, so let's do that first. And then after we do that, we'll be able to make a model, and we'll predict the number of wild beavers in 2025. Okay. So let's start off with the doubling period. Now, since we started with 20 beavers, so I like to use a very basic model, y equals CEKT. That's your classic natural exponential growth model. I don't really need to know that this is 20, yeah? Because look, as we see in many of these examples, when we're finding the doubling period, I'm starting with 20, and so the new value will be 40, yeah? But this always happens. It really doesn't matter that we started with 20 beaver. We started with 20 beaver, that's still always going to be 2. Yeah, so whenever we're finding the doubling period, the initial number of beaver, or whatever it happens to be in the problem we're studying, really doesn't matter, all right? It will matter at some point when we finish off this problem, but let's go ahead and do that. All right, so let's find the doubling period. And so how long did it take to double? So we're trying to find t, yeah? But first we need to know k. First we need to know k. So we're going to use this fact here. 2011, remember 1946 now is 0. So 2011, we could just subtract 1946 from 2011, and that will give us, what's that, 60, now let's do it old-fashioned style. That's a 10, that's a 5, and that's a 6, 65 years. If you're not sure of your arithmetic skills, keep your calculator handy. 2011 minus 1946 and you'll see that it is in fact 65. If you don't believe me, calculator says 65. So 65 years. So we have y equals CEKT. We don't know K, but we do know T is 65 years. So 200,000 beaver, starting with 20 beaver, and that took 65 years. So now we can find K. Then we could use that K to find the doubling period. So this will be doubling, or the doubling time, it's also known as. So we divide this one by 20. That'll give us 10,000. Yeah, 10,000. E to the 65K. All right. I love this natural exponential function because it gives you what we call the log natural, or the ln. So the ln of 10,000. I remember it as log natural, or the natural log. Sorry about my cursive. That would be 65K. So we have the natural log of 10,000 will give us the 65K. We'll divide both sides by 65. And this will give us our K. So we got 10,000, the natural log of 10,000. It's about 9.21. If you can see that, the camera's way over there. 9.21 divided by 65. And we get 0.1416975. That's enough. You could probably get away with just 4 of these decimals, maybe round this. So I would say, just to make it easier to write this down, I would write it as 0.1417. That's our K, and then we have T. All right, so this is our K. Don't forget that. We're going to come back to it in a minute. Now let's answer the question about the doubling period. So now that we know the K, we can do again the natural log. And we could say the ln of 2, because we're doing doubling period now. It's not very easy to read. Ln of 2 is equal to 0.1417t. So t is ln of 2 divided by this decimal 0.1417. Let's see how long it took for the beaver to double. So we got ln of 2 divided by 0.1417. Approximately 4.89. I'd probably just round that to the nearest year. Again, depending on how I phrase the question, if I said nearest tenth, I guess it would be 4.9. But I mean, once you got to 4.9, you might as well just say 5. So about 5 years is what I would accept as an answer. So that's the doubling period. It takes about 5 years. It took about 5 years for these 20 beaver to double, right? Now that might not seem like, oh, that's going to be a problem, right? Because you started with 20 and 5 years later there's 40. But watch what happens. When we go to predict the population in 2025, all right, so we'll do 2025 minus 1946. Let's do it old-fashioned style. So that's 9. Let's see, that's 19. That's 79 years. So now we come over here to predict the number. We want to know what's the Y value if we started with 20 beaver. Now we've got this K value, which I told you not to forget, 1417. And then we're going to plug 79 years into it. So we're basically taking this model here and we're plugging in the K value that we have now, our constant, growth constant. And then we have the number of years, 79 years. I really don't want to screw this up. So let's see, 25 minus 1946, 79 years. All right, and so now let's calculate this. Once we have the model does all the work for us. So we got 0.1417. That's our K. I could use a more accurate decimal, but I mean, this will do just fine. Times 79. So that gives us 11.19. I'm not going to round at this point. Now I'm going to do E. Oh, I screwed that up. So I got 11.1943. Sorry, you're watching me screw this up. And then do E to that power. So that's 20, and then this E value, exponential value, becomes 72,714. It's 0.7. Doesn't matter, I'm going to round it now anyway, and then I'm going to multiply that by 20. And I get 1,454,296. I'm rounding to the nearest whole beaver. That's a lot of beaver. 1,454,296 beaver. That would be the prediction currently. If you're watching this video in 2025. If you're not, you could certainly do a similar version of this. The original values that I started with are true values. And so I just wanted to show you that and give you an idea of how exponential growth can really get out of control, and how sometimes when we think we're solving a problem, we just create a new problem. Well, that's it for today. I wanted to keep this short. We got more exponential functions and more applications coming soon, but until we meet again, I'm Dr. Jordan, and I'll see you on the internet.